So for our next topic, we're going to get into overhead line construction and modeling, and I'll also work a few examples at the end. Before I get into the topic, at the last lecture, John Guida was talking about substations and primary feeders, and he's talking a little bit about design issues. And I wanted to show you an old diagram of a Carolina Power and Light utility system that was in an early edition of Bill Stevenson's textbook, Elements of Power System Analysis. And many of you probably heard of this textbook before. It's kind of a famous book on power system components and power flow, short circuit analysis, and things along those lines. But anyway, at the very beginning of one of the early editions of this textbook, and this goes back to like 1955, they had a pull-out diagram, and what that showed was it showed this Carolina Power and Light transmission system. Of course, since then, the company's been purchased by Duke Energy, and sometimes this is referred to as Duke Energy Progress. But what you see is the transmission infrastructure that existed about 70 years ago, and you can see that a lot of this was in the 100 kV level. And so back then, 100 kV was the high voltage, and then they would have sort of like transmission, or what we sometimes refer to as subtransmission, like at 22 and these other lower voltages as well. And so we didn't have the high voltage infrastructure we have now because we just didn't simply have the loads back then. I mean, this would have been somewhat shortly after World War II. And so anyway, I thought this was just kind of interesting just to kind of show, basically what we had a number of years ago. And if you're going to compare it to what we had today, there's a lot more transmission infrastructure, obviously, to support the growing load. But this is before there was a Research Triangle Park, and before like schools like NC State were really kind of built up in size. And this was a lot more of a rural area back then. So anyway, I just thought I'd point that out. You would probably nowadays not see a pull-out map of utility infrastructure because those would be kind of considered to be confidential information nowadays. But back then, this would be the sort of thing you see sometimes in textbooks. So anyway, what we're going to do is we're going to talk about overhead, and in the next lecture I'll get into underground cables. And we're going to start off by going through construction, some of the conductor characteristics. So talk more about what's the physical overhead element look like. And then we'll get into doing the modeling. We'll be developing what we would call an impedance model. And then in the last part, I'll go through some examples and show you, what this would look like in a computer program like MillSoft Windmill. So why do we need feeder impedance models? There's a number of different reasons for it, but this is the primary element, like in distribution system analysis. We've talked about transformers so far, but the reality is a lot of times when we're doing power system calculations, we don't even model the voltage drop across the transformer. Mostly what we're interested in is how does the voltage change going from the substation to the various endpoints up to the transformer. And so we typically kind of focus on the what we call the primary voltages. And so a very important thing is to be able to do voltage drop calculations. We want to make sure the voltage doesn't get too low on the primary. And later on, we get in voltage regulation. I'll kind of talk about a budget, like a voltage budget for how much drop we could afford to have. We can also calculate I²R losses because these overhead lines have resistance. And so we would do loss calculations around that, which would be kind of based on I²R. Then we would be interested in knowing like whether we might possibly be overloading some of these lines. So we would be looking at whether we have overloads or not. And then finally, another type of analysis that's used for protection is to do short circuit studies. And so instead of calculating what the voltages are in steady state, we're more interested in knowing what sort of currents would flow if we had like a fault on different parts of the circuit. So as far as the construction types, what we've got is we've got 1, 2, and 3 phase types of constructions. Three-phase would be what we would see coming out of the substation. So at the top of the feeder, we would see this three-phase, or what you're going to have below it is you're going to have a ground wire. This is our ground right here. And every so often, what we're going to do is we're going to tie this to a stake in the ground and make a connection to earth. We've also got two-phase. We've also got single-phase. This shows us a case where we kind of like these standoff arms, or you could have like a cross arm sort of a arrangement. In the case of the cross arm, you can see you have these little pin type insulators that support the wire. What's going to be important in this case is what are the construction characteristics as far as the distances between the wire, because it's the distances between the wire that's going to define the inductive reactance of our overhead line. And so this is a construction drawing here. This shows kind of like you have a cross arm. You have these insulators that we're going to place the conductor on top of. So the conductor is going to be on top of here. We're going to have a place where we can attach a neutral wire as well. So this would be what we refer to as a four-wire construction, where these insulators would have enough size to them or length to them to make sure that we're not going to have voltage flashover, right? What's kind of interesting about this particular drawing, as far as having all these distances that we could use for doing the calculations, is this is from a bulletin that comes from the United States Department of Agriculture. And you might be wondering, well, why would Department of Agriculture have this type of information? And the reason they have this information is the Department of Agriculture promotes rural electricity in the United States. So a lot of the cooperatives are getting funding or getting assistance from the Department of Agriculture. And so at the very, very end of the PowerPoint slide deck, there's a number of references to these different bulletins from the US Department of Agriculture that has all this type of information, like on line construction and designing substations and things like that, which is extremely useful because many times this would be proprietary if we're talking about like this sort of information coming from an investor-owned utility. So it's very useful for the different voltage levels that you would have all this construction information if you actually wanted to build your own distribution system. So anyway, as far as what goes into the construction here, as far as whether we use wood cross arms or use metal or standoffs, whatever, or what kind of conductor size we would use, if we use like really thick conductor versus narrower conductor, depends on a lot of different things. Basically, these lines have to hold up to different weather conditions. And so we'd have to worry about wind loading. We don't want to blow over if there's like a hurricane, ice loading. If ice freezes on the conductors, we don't want the weight to pull the line down. There's basic insulation level. So if we have like a lightning strike, we don't want to have too many voltage failures where the voltage rises up to the point where it flashes over the insulation. Now it's not feasible to make it so it doesn't flash over at all, but certainly we can eliminate a lot of the different disturbances that would maybe cause flashover. We would have fault tolerance, and so we would want to make sure that we have a construction that's not too susceptible to trees, maybe branches falling in or animals getting hung up in the conductors. Work methods, we want it something that's easy for crews to work on from their bucket trucks. And then we get into impedance. And so what we can actually do is we can actually have different impedances depending on what sort of conductors we would use and how we have distances between the wires, which is what we're going to be focused on. There's also aesthetics. And what I mean by aesthetics is how nice does it look? And so there's some constructions that would look better in a commercial area than others. And so these are all sorts of different things we can take into account. We're going to be mostly focused on this impedance characteristic. So we have different sort of wires we could use. These wires are made out of different materials. Now you might think about copper as being the type of wire that might be used because you normally associate copper with being a good conductor. However, copper is generally a lousy conductor to use for overhead. And the reason being is it has a low resistance, it has lower I squared R losses, but it's very heavy, it's very expensive. And the other thing too is it's kind of a soft material compared to other type of materials. And so we may use copper, special types of copper alloys for the smaller wire sizes, or we might use it for grounds. But generally, if we were talking about like overhead coming out of a substation, we would not use copper for that. It doesn't have the right strength characteristics. And so what you would see instead is either aluminum or some type of a mix of aluminum and steel, let's say. And so you'll have different sort of conductor types, like what we refer to as all aluminum conductor. So this has a pretty decent conductivity to weight ratio. Maybe it's not as good a conductor as copper, but it's good enough for what we need, but it's very strong. And you'll see a lot of these are going to be stranded. You know, they consist of a lot of small different strands of aluminum wire. You're going to see what we refer to as aluminum conductor steel reinforced. So we have like a steel core. So this would probably have one of our better strengths associated with it. And then you have alloys, you know, they call this all aluminum alloy conductor, right? So this alloy conductor is what you might have if you have like a lot of possibilities of corrosion, if you're near the ocean or near like an industrial site where there might be pollution that could corrode the conductors. You know, this is something you might want to use. And so copper, again, even though it has the lowest resistance, is not really the best material for overhead for the larger conductor sizes. We're going to be interested in what the characteristics are of these different types of conductors. And so there's a size number, and we'll get into this just a little bit about what KC mil versus AWG refers to, but these are sizes. This gives you an indication of the thickness. As you go down the table, these are larger and larger wire sizes. You'll see these are made out of a number of smaller strands, and so we kind of wrap the smaller strands together to form a cable. There's a cross-sectional diameter, and there's another number here called GMR, which we'll get into a little bit. It stands for geometric mean radius. It's not an actual radius, but it's a radius-related number that we use for calculations. And then you'll see different types of resistances. And you'll see a DC resistance, which isn't really all that useful because we're going to operate this at 60 hertz. But at the fundamental frequency, then you see you have these numbers at 25, 50, and 75 degree centigrade. And this would be the temperature of the wire. And where this comes into play, if I have a lightly loaded wire, there's not much heating effect. And so maybe we're going to be around 25 degrees C or so. If you heat the wire up, then the wire resistance actually goes up a little bit. And so 50 degrees C would be the number typically associated with heavy loading. And normally we go back and forth between 25 and 50 degrees C. 75 degrees C is a little too hot for what we need. But the reason we're doing this is then if we go to the higher operating temperatures for the conductor, then we're going to have a higher resistance. And so we would actually want to model this. And then there's going to be things like strength or weight or ampacities for the cable. In the short book, they don't show the ampacities in this particular table. We would have to go to another table. And so this is where some of the tables in Kersting's textbook would be useful. And we use this as a reference in the class, where again, you've got the size, and this is all in terms of increasing size. And then you have different types of material like ACSR or copper, whatever. And then you would have some information about whether it's stranded or not, number of individual strands. And again, you have the same diameter, GMR, resistance information. And then it would have a capacity in amperes. And so this would be the amount of current that this could carry under normal sorts of conditions. And you want to make sure that you don't operate this above the capacity limits for too long. Otherwise, what happens is that this cable is going to heat up and it's going to start to sag. And these can sag for kind of a short period of time, but if you leave it heated up for too long, the sag could become permanent and the cable's permanently damaged in. So you have some ability for overloading, but again, the cables are going to sag. Maybe they sag into a tree and cause a fault, or they could actually sag and they could actually damage the cable. And then this is the rest of the table. And you note that we go from these, what we call American wire guide numbers, which are like integers, up to these other size numbers, where these are going to be in terms of circular mills, which I'll get into in just a little bit. And so if you go to the vendors of these cables, they give you all this information. They'll actually give you a lot more detail on this as well. But this is the information that we're going to use for coming up with the modeling. So as far as the cross-sectional area, the thickness of the cable, again, there's a couple different ways we can do this. One would be to do this in terms of circular mills. And so basically, if you think about having a small wire, this cross-sectional area is given by pi r squared. And so if you had a small little wire that had a radius of 1/1000th of an inch, then we would say that that's one circular mill, right? I shouldn't say one circular mill, but that would have a circular mill of 3.14 times 10 to the minus 6 inches squared, all right? So one circular mill in this case is equivalent to this cross-sectional area. If we talk about, like a common sort of a cable, like a common cable would be a cable that had a cross-sectional area of 336,400 circular mills. Okay, so again, one circular mill corresponds to this pi r squared value, 1/1000th of an inch radius. And we usually, instead of using this big number all the time, we talk about thousands of circular mills. And so instead of saying 336,400, we would just simply call this a 336 MC mill. M stands for 1,000 in this case. Or we just say this is a 336, all right? Now, if we have smaller conductors, we use something called American wire guide. And those are integer numbers that would correspond to the size of the wire. And so actually there's this little circular thing you can get. And you can see that for the smaller numbers, this is a small diameter wire. And you get up to the larger numbers, then you can have all the way up to a knot with this simple, one knot with this simple guide here. A lot of times what you're going to see once you get bigger than 1, 0, or we call that an aught, then you're going to have what we call like a 1/0, 2/0, 3/0, all the way up to 4/0. And these are also kind of common cable sizes. You're going to see utility feeders for like the primary or the lateral circuits. And so you can relate these to circular mills, but typically when we talk about these, we usually would just talk about like a number 4 wire, number 1 wire, or a number 6 wire maybe. And you could see like in a table like this, then what would be kind of the equivalent diameters in these situations. One of the things when we talk about aluminum conductors or these ACSR types of conductors, I should say, with the steel core, is the steel core is in the middle, and this gives us strength. And then we have the aluminum conductors on the outside of the core, the steel core. The reason we could do this is when you operate at 60 Hertz, there's something called skin effect, where the current density tends to be higher on the outside than on the inside. And so what this means is because of skin effect, when we go up higher in frequency, we don't have as much current density in the middle here. And so it doesn't have as much impact on the net resistance as you might think. So as far as conductor selection factors, a big one is what kind of current can it handle. You have to have a bigger conductor if you want to handle more current. And so utilities coming out of the substations would typically have these really large conductors. And when you get further away and the load drops, then we go with the smaller conductors. The other thing you would worry about is mechanical strength. And so the thicker the cable, obviously, the stronger it's going to be. And as far as the strength characteristics we have to consider the span length. And so, you know, what's going to be the distance between the poles, because then there's going to be a certain weight that has to be carried by the conductor. There's the ice loading. If you're going to get ice on here, you want to make sure it doesn't snap. And then there's wind loading, where you want to make sure that you have like hurricane winds or storm winds, that it doesn't knock the cable or break the cable, right? Corrosion, as mentioned, is another factor. And then you get into economics. And so the thicker the wire, the more this is going to cost. If you use thicker wire, turns out you'll end up with less voltage drop, you'll end up with less I²R losses, but you have to pay more for that wire. And so basically you would do some economic analysis around this. And then based on the loading you expect to have and your cost of losses, you would figure out, well, you know, for going from the very, very thick conductor to the skinnier conductors, you know, which one would I want to use? And usually utilities standardize on certain sizes depending on the circuit loading. Okay, so let me go ahead and stop here for this part, for part A right here. When I come back, then what we'll do is we'll talk about line inductance and how we can actually do these modeling calculations